last couple lessons, confidence interval. And the formula that you get on the formula sheet for the exam looks like this. The confidence interval is a statistic plus or minus a critical value, which is the number of standard deviations or standard errors, pardon me, depending on our confidence level. Okay, this will change. If it's a confidence interval of 95%, it'll be 1.96. If it's 99%, it's going to be a little bit higher. If it's 80%, it's going to be a little bit smaller. And like I said, we'll talk about how to figure those out in this lesson. And then you multiply it by the standard error. Remember, that's the same thing we called it when we were going the other way, standard deviation. Okay, but that's what it looks like on the formula sheet, yes. Just the critical value. Okay. Now the way that we looked at it, and another way that I showed you, remember, statistic is the same as the point estimate. So if it's a proportion confidence interval we're doing, then it would be whatever the sample proportion we got. That's what would go here. Okay. So like if the sample proportion was 45%, we put 0.45 there. Okay. If it was 27%, we put 0.27 there. And like I said, this is the number of standard errors times the standard error. Okay. Just showing you different words that we use. Now, in the last lesson, we talked about the water crisis in Flint, Michigan. And here you can just see a timeline of what happened. Okay. So it all started in 2014 when they thought they were saving money by switching water supply from Detroit to the Flint River. But Flint River was not a great choice because in 2015 it resulted in declining water quality. But the mayor says, oh no, it's safe, it's fine. And then 2015 comes along, and then this guy from Virginia Tech, okay, started testing the water systems, and it turned out that it was not good. It was above the more than 10% of homes had prominent lead levels, which was leading to sickness and even some deaths. So we're going to kind of look at this one again, okay? Because we did do a sample, and we talked about how to find the confidence interval. So this is a slightly different sample, okay? So imagine this is not what they actually did, okay? But imagine they sampled 66 homes. And of those homes, 11 had prominent lead levels. So what we want to do is we want to calculate the sample proportion of homes with prominent lead levels. So 11 out of 66. That gives us approximately 0.167. Had prominent lead levels in the sample. And of course, we were answering these follow-up questions. Does this evidence convince you that more than 10%? Well, even though this specific sample is more than 10%, we could have got it by chance alone or sampling variability. Okay? we could have got this result. Chance. In other words, sampling variability. Different samples will produce different results. So we're not convinced yet. Seems it might be the case, but we're not convinced. So this is where we've got to take our random sample and our sample size and create a normal distribution at the 95% confidence level to see what's the probability of getting the result like this. And in order to do that, we create a confidence interval. Okay? To say that, yeah, this is what we got, but after we do all these calculations, our result could have been anywhere from here to here. So technically, we consider all the different random samples you could take, and there are many of them. There are many, many ways to get 11, or sorry, to take 66 homes, and calculate their sample proportion. It could be 0.167. It could be another number. It could be another number. There's all sorts of different samples. So what we want to do is think of all those possible sample proportions, okay? Find the average of them, find the standard deviation, which we call standard error, and see just how likely it is to get this. Okay. So for this, okay. Our sampling distribution, sample proportions is going to be normal. The average of all those samples is going to be the same as the sample proportion we got, 0.167. That's because that's the only value we have to use right now. And the standard error is going to be calculated, you see there. So in our example, remember it's 0.167 times 1 minus 0.167 divided by the sample size of 66, which is going to give us approximately 0.046. And we need all of this. We need to know that it's normal. We need to know the mean of all the sample proportions, which is the same as the sample proportions we took in our sample. And we need to know the standard error in order to do normal calculations. And then just as a review, why do we use p hat instead of p? Because we don't know p, right? This is what we're sort of trying to estimate. So we're going to use that, yeah.
This is just like a random question.
Sure.
Call for build it. I knew for not using like instead of putting approximation, the equal sign.
No. I read it somewhere, or I heard it somewhere, some discussion forum that it was not an issue. Okay, so why? So we don't know P. We don't know the true proportion. So we use our best guess. Which is the sample proportion of that p hat. And because we don't know p, like remember in unit 6, we did know p. We were trying to figure out p hat. Now we're going the other way around. So when we knew p, we could call it standard deviation, right? When we knew the actual population proportion. But because we don't know it, that's why we just switched the name to standard error. Okay? So also, we use standard error for the same reason, because we don't know p, instead of this notation. Okay. So let's assume we remember we have to meet certain conditions, random, 10% condition, and remember this normal is, you're either told that it's normal or it's a large sample, which means p hat must be greater than or equal to 10, and sorry, n times p hat must be greater than or equal to 10, and n times 1 minus p hat must be greater than or equal to 10. That central limit theorem only applies to means, and we're not talking about that here. Okay. You're going to have to write small, because I thought I took this stuff out. Don't let that diagram, so I replaced it with my own, and I'm not ready to talk about that just yet. So I'm going to sort of try and squeeze this stuff in here. Okay. Okay, so we've got a normal distribution. I'm going to make it a little small. We've got our mean of all the sample proportions, which is 0.167. Okay. We've got our standard error, which is 0.046. So we keep adding those to the 3 notches on the right, and we subtract those for the 3 notches to the left. So the values we get on the right, 0.213, 0.259, and 0.305. And on the left, when we start subtracting that standard error, we get 0.121, 0.075, and 0.029. And remember, we're trying to find the range, the interval, that allows us to be 95% confident, or 95% of this area. And what is 95% of this area? Well, we always said it was 2 standard deviations. But remember I told you it's 1.96. It's slightly inside the 2 standard deviation notches. That's 95%. So all of those sample proportions, when we take several samples and average them out, and we want to see what fall within 95% from what numbers. Okay, so that's 95%. So remember the confidence interval that I wrote at the beginning. The confidence interval is the point estimate or the statistic that we use, which was our sample proportion, plus minus the margin of error, which is made up of the number of standard errors, which I told you for 95% is 1.96, times the standard error itself, 0.046. And then when you do the multiplication, you get 0.167 plus or minus, that works out to 0.09016, which gives us an interval that on the low side is 0.07684, or about 7.7%, all the way to 0.25716, or about 25.7%. Okay. So even though we got 16.7% to be 95% confident, we have to expand that. Okay. It could be anywhere from 7.7% to 25.7%. Could be the population proportion. Okay. So interpret our 95% confidence interval. Well, remember, we said we are 95% confident. That, and then write your confidence intervals, 0. If you want to round it, that's fine. Okay. 0.7684 to 0.25716 captures the true proportion of homes with prominent lead levels. Now, here's where you got to look at your confidence interval to answer the next question, the next part. Is there convincing evidence that Flint water system violates this rule? Okay. Remember, it's 10%, right? So what you have to do in a situation like this is you say, okay, does 10% fall within the interval? Is 10% a possibility? Yes. And because it's a possibility, we don't have convincing evidence. They're violating. Because we could get 10%, we could get 9%, we could get 7.7%. Okay? It's possible to get those. Most of them are over, but some of them are under 10%. So because of that, we're not convinced. Okay? So no, we don't have convincing evidence. Because the 10% rule for water safety falls in the confidence interval. If it was completely outside, if it was completely above, then we would have convincing evidence. But it's not. So we don't. Okay, so this was sort of the longhand way that we calculate confidence intervals. And another way you can see it to calculate confidence intervals This is the point estimate or the statistic. This is the critical value, the number of standard errors. This is the standard error itself. And this is how we calculate the standard error. Okay? So the Z star is the critical value. And it does relate to Z scores that we did earlier in the year, standardized scores. Okay? So that's why in the previous lesson, I called it a Z interval when we did the big long solution. I call it a Z interval. That's why it's called that, because Z is referred to as the critical value. Tells you how many standard errors you are. From the center. And like I said, similar to a Z score. That's where we get it from. Finally, it determines the confidence level. Okay, this number depends on our confidence level, or what we are, the percent confidence interval we're asked to find. And right now, all we know, because all we've done is 95%. We knew it was 2 from earlier in the year, but I told you technically it's 1.96. Here's why. Okay, so imagine we want to make a 95, we want to find 95, or we're given 95% of the area, and we want to find these notches, right? Because that will tell us the number of standard deviations. So remember, we always said it was 2, okay? So here, this is 95%. I want to find these, but right now I don't have any values for these. Well, what I want, the values that I can put in, okay? Don't I want to find the number of standard deviations? So wouldn't I call this 1 standard deviation, 2 standard deviations, 3 standard deviations, which means what would the mean be? 0. And this would be 1 standard deviation to the left, or -1. 2 standard deviations to the left, 3 standard deviations to the left. So those are the numbers I use for the mean and standard deviations, because I'm trying to find the number of standard deviations. So I need, these are unknown. Okay? So I need to find them. And it's a normal distribution. What percent is that area? 2.5, because these two are 5, so this is 2.5. Or 0.025. Do you remember how to find the value if we're given the area in a normal distribution? Not normal CDF. That's when we're finding the area. We're going backwards. Inverse norm. So to find this, I'm going to use this. Inverse norm. The area is 0.025. The mean we've established is 0, and the standard deviation is 1. So when you get that, and you round it to 2 decimal places, you're going to get -1.96, which means on the other side, it's going to be the opposite, +1.96. So how many standard deviations away? 1.96. So we find this one, and it's always going to be a negative value. Okay? But remember, we're finding the number of standard deviations away. So from here, it's 1.96 from 0. So that's why we get Z star is equal to 1.96. We just remove the negative. That's where it comes from. So that allows us to find any percent confidence interval. Let's say an 80%. Well, we're always going to use 0 as the mean and 1 for the standard deviation, always when we find this. And we need to find what's, so 95% is there, I don't know, 80% probably somewhere around here, maybe. So I need to find these. It's here. I don't need to find this one because it's going to be the opposite of this. This is going to be a negative value. This is just going to be the opposite. But in order to do that, I need to establish how much area is this so that I can use inverse norm. This would be 10%, right? Yeah, because it's 20%. If it's 80% here, half of that. So yes, 10% for 0.1. We have to use that when we have to use the decimal area when we punch it in the graphing calculator. So then what we would do is just inverse norm. Area is 0.10. Mu is 0. Standard deviation is 1. Go to 2 decimal places. And when you do this, you'll get negative 1.28. But remember, that's the value of this, but the number of standard deviations, the actual critical value, or Z star, is positive 1.28, which means it's positive 1.28 standard deviations away. Which makes sense, because it has to be smaller. If we did a 99% confidence interval, it's going to be larger than 1.96. So we can do any confidence level we want. So if we go back to that example, and let's say we wanted to find an 80% confidence interval now. Okay, first of all, is an 80, we know what the 95% confidence interval was. It was what, 7-something%, 25-something%? Okay, do you think this one's going to be smaller or bigger? Do you think this interval is going to be smaller or larger? Look at the 2 diagrams. Do you think that it's going to be smaller or bigger? Smaller. It's going to be a smaller interval. But the trade-off is we're less confident, right? We can go high confidence, but then our interval is going to be bigger. Okay, there's always a trade-off between the two. It's generally agreed upon that 95% is a good interval to use. That one will be used the most, but it's not necessarily the only one. So to calculate this one, to find our confidence interval, it would still be 0.167 plus or minus, and then all I'm doing is changing this. What is it, 0.46? Yeah, 0.46. Which gives us 0.167 plus or minus 0.05888, which gives us 0.10812, 0.22588, or about 10.8% to 22.6%. According to this one, there is convincing evidence, right? Because all the values in the confidence interval are above the 10% threshold. So you can kind of see how statistics can get manipulated to answer a question that you want, like to answer a question a certain way. So from here you could say, but you do have to say we're 80% confident. So when you're looking at something like this, you want to look at the confidence level. Because if it's lower, it's like, well, I increase that confidence level, this could shrink, or sorry, this could expand, which means that I could get results lower than 10%. Now I have even better news. Because you don't even have to do all that work. Okay? Like I said, I wanted to show you how we do it by hand, how we break it down, but there is a way that you can use your graphing calculator, punch in certain values, and it will calculate the confidence interval for you. It will calculate the standard error for you. It will calculate the critical value for you. Everything. And this is how you do it. So this is important. And you can use this from now on if you want. You don't have to, like some students, they like using the longer approach. Other students just like using this because it's nice and straightforward. So remember, N was 66. The number of homes with prominent lead levels was 11. Okay, the confidence interval is 95. That's what we started out at the beginning. So if you go to, and all of these things now, confidence intervals, hypothesis tests, which we're going to talk about next week, you all find them when you go stat and scroll over to tests. That's where they all are, because they're all tests, we call them. And we want to choose because it's a one sample proportion interval. That's why we want to choose one prop Z-int. So if we go there, you're going to be asked for three things. X, that's the number in your sample. Not the total sample, not the sample size, but the number of whatever it is you're finding. In this case, it's 11. Prominent home, or number of homes with prominent lead levels. N is the sample size, 66. Sea level as a decimal, 0.95. Calculate. So notice right there. It's slightly off, obviously, because we did some rounding here. Okay, but it's pretty much identical to that. What was what? What? I'm not sure what you're asking. There it is. So that was quick. Yes. Like here, try this one. Go back into tests and just change the confidence level to 80% or 0.8. That's all you have to do. And you should get something that's very close. So we got in here, we got 0.10788 to 0.22546, very close. Okay? Because remember, we rounded the critical value, didn't we? They don't do that here. So it's going to be slightly off. Margin of error. Notice it also gives you the sample proportion and the sample size as well. Okay, so let's finish this up. Is the interval narrower or wider? It was narrower. We're talking about 80% versus 95% level or confidence interval. Narrower. And does provide convincing evidence. Because all values in the confidence interval are above 10%. So the confidence level can dictate the size of our confidence interval, right? You saw that. And remember, I talked about this in a previous lesson. So can the sample size. So this was our study. This was our mock study today. And this is kind of how it looks. 95% confidence. And then we got, this was rounded to the nearest percents, 8%, 26%. Okay? We got more precise than this. And we were this many standard errors away here, this many standard errors away here. And that was a sample size of 66. Increase that sample size. This was the actual study. The sample size was 252 homes. The actual number with prominent lead levels was 42, which actually works out to the same percentage. But because our sample size is bigger, it's going to narrow the confidence interval. Because bigger N means smaller variation. Okay? So why did the actual Virginia study get a narrower interval than our Mux study? Well, sample size is larger. That's sort of using intuition. Using the formula to find the standard error. Remember, it's p hat times 1 minus p hat divided by n, and then we take the square root. Well, it makes sense that the bigger this gets in the denominator, the smaller it will become after the division, right? I mean, like if you think about it, 1/10, okay, is smaller than 1/2. because it has a bigger denominator if the numerator is 1. Okay. So this gets smaller as this gets larger. And then going back to the actual study, does it provide convincing evidence? Well, again, you just have to look at the confidence interval. Everything's above 10%. So yes. So that answers the question here. Yes, all values are above 10%. Or all values in the CA are above 10%. CI are above 10%. That constitutes huge. That's water crisis. Okay, the last thing we're going to do. And it's a question you may have wondered about. How do we know what sample size to pick when we do something? Like if we're asked to test a claim, if we're asked to find a confidence interval, how do we know what sample size to use? It seems like in general, the bigger the better. Okay. But remember, you can only get so big because it always has to be under 10% of the population, right? So you can't just go infinitely big. There's a trade-off. So a higher sample size, you're going to get more data points. It's going to take out unusual sample proportion values, so they are less likely. And there's less variability. It gets tighter in the sampling distribution. And the confidence interval is narrower. Okay. So the critical value, that's determined by the confidence level. 95%, 80%, 86%, 99%. Okay. The standard error measures the variability or the spread in your sampling distribution. Okay. Which means the typical distance from the true proportion. And like I say here, the higher n gets, the lower the standard error. Now, this is a question you could face. You could be asked to find what's the sample size. What sample size should you choose? And you're going to use the margin of error formula. Okay. Remember, the margin of error is the portion where it's the critical value times the standard error. Or in other words, the critical value times square root of p hat times 1 minus p hat divided by n. So here's the information you need to find a sample size. You need to establish a margin of error because you need to put a value in. We need values for everything except for n. So we need a margin of error. We need a critical value, which we can get from the confidence interval level. Okay. And we need some sort of estimate as to the number of homes. In this case, the number of homes with prominent lead levels. So for here, our margin of error is 3%. We want a 3% margin of error. What's the critical value of 95%? 1.96. And here, well, what's p hat? 0.167. That's what we anticipate the number of homes with prominent lead levels will be, the proportion. And I want to figure out the sample size. Well, algebra, baby. What do we got to do here? What do we got to do here? Well, first of all, we can simplify this a little bit. Zero 0.167 times 1 minus 0.167 gives us about 0.139. Got to get in by itself. Really? You want to square both sides first? Get rid of this first. And we're going to get we're going to get 0.03 divided by 1.96 gives us about 0.05 equals square root of 0.139. Then now square both sides. We'll take out the square root. So 0.015 squared is 0.0003 zeros. 0.225 is equal to we're almost there. I heard some mumbling. Do you know that in an equation like this, you can just switch these two? Because really, what are we going to do? We're going to multiply both sides by n to get rid of this. And then we're going to divide by this to get n by itself. So really, to find n, we're doing this to by this. So n is going to be 0.139 divided by 0.0025. Remember, we're finding the sample size. So go nearest whole number and always go higher to be safe. 618. So really, we would say this. We could go bigger as long as we're within 10% of the population. That would be the sample size. What happens if you have no idea what the proportion is? Okay. That's the last thing. What happens if you have no idea what the proportion is, which often happens? Okay. What you do when you don't know, use 50%. because that will give you the most conservative number, the best estimate. Okay, so when you don't know, use 0.5 when you don't know. Because that will give you the maximum value for this, which is the most conservative estimate. Okay, I strongly suggest, because it's going to be a state plan do conclude problem, that if you do question, and I'm going to talk about it Monday, do question 4 definitely from lesson 7.3 practice, because that will be a common question.